So, what to say about a meeting that we finally can organize in presence in Milan? I think it's the third meeting we are having in the Department of Mathematics since the end of formal restriction for pandemics. So I'm really happy to see many people in this classroom and many young people as well, very happy of that. So what to say about issues like sustainability and statistics is not my field, but I can say that sustainability is a sort of dogma, it's a sort of also fashion, let's say, if it is seen in a superficial way. But actually, the attention to sustainability is a thing which many of us, and especially the group of statistics at my department, did have in the course of the year. Actually, I also had, working on satellite imagery for many years, this kind of attention. It is rather a matter to understand that we were, in a sense, doing sustainability without knowing that. For instance, I've seen that we have a talk on satellite imagery for the approach to fire control and so on. So this is a classical, I think, example we can take about works which can be usefully rearranged in the field of sustainability. So sustainability and statistics, what I can say about sustainability and statistics, well, what I can say about sustainability and mathematics, because we were speaking before with the president that scientific multidisciplinarity fields are the most important now, and of course mathematics is entering in so many fields, and statistics is entering in so many of these fields, which mathematics is becoming more and more important. So yes, there is a strong link about sustainability and statistics, and yes, we are interested in making it stronger and in enhancing our collaborations with other fields, other related fields. So I think it's enough. I really want to welcome you in Milan at this meeting, and I leave the floor to the president of the Italian Association.
Okay. Thank you so much. Before starting, I would like to thank Professor Laura Sangalli for organizing this event verso il Festival della Statistica. As most of you know, next September in Treviso, we are organizing the Statistical Festival. From the 16th to the 18th September 22, Treviso will host the 8th edition of our festival. We are organizing many talks, interviews, shows, and games addressed to non-statisticians to promote statistical literacy. I'm very happy to be here in this department MOX that since 2002 promotes research in the field of mathematical modeling, data science, and scientific computing in science and engineering. The title of today's conference is very promising because environment and sustainability are two keywords of great interest for PNRR, as many colleagues are obtaining interesting results in these fields. We will listen to interesting lectures about wildfires, vegetation recovery through satellite remote sensing, and functional data analysis by Pedro Delicato from University Politecnica di Catalunya, my friend Alessandro Fassò from the University of Bergamo will speak about statistical modeling of COVID-19 impact of marine carbon emission, and Professor Cesare Secchi will present a new perspective on statistics for the environmental and sustainability. As you know, the Italian Statistical Society was founded in 1939 to address social problems through the collection and the classification of facts, leading to many developments in the collection of data, the development of methods for analyzing them, and the development of statistics as a profession. Nearly 80 years later, an explosion in computational power has led, in turn, to an explosion in data. We outline the challenges and the action needed to exploit those data for the public goods and to address the step change in statistical skills and capacity development necessary to enable our vision of a world where data are at the heart of understanding and decision-making. As a society, we already know we have more data available than we have ever had. Advances in technology mean that increasingly more data are accruing, whether in health records, on mobile device application, and from our electronic payments for travel and day-to-day purchases. That offers huge potential for good, but also limitless opportunity for misinterpretation or misuse. The spatial analysis takes on new measuring. Recent development mean that data generated on social media and mobile phone data, which contain geographic locators, can be used, for example, to estimate the size of crowd or to study wildlife population abundance with environmental sciences offering fresh challenges. The use of such data quickly leads to question of privacy and who should have access to data for user beyond this primary purpose. This is often an implicit assumption that data are owned by an individual, but much data are owned by more than one person. For example, genetic data, at least implicitly, give information about close relatives, and data on visit to a general practitioner are relevant both to the patient and to the management of the practice. I prefer to think of data to the patient and to the management perhaps as people data rather than our data or my data. It is a little like tax. We all contribute to various ways when we can, and we benefit when we need to. To meet the biggest challenges facing society, we need to increase statistical and data science capacity in order fully to be able to use appropriate methods with the data that are available today for the public good. As well as individual need a greater depth in training, there is an even bigger increase in the number of people who are needed with these skills. Some of these will be in traditional statistical mold, some more mathematical, others will be data scientists, but many more needs take skill as part of their portfolio, either to carry out, to work, or to be able to understand and use them intelligently as part of their work. So I hope that this new edition of this verso il Festival of della Statistica can be a good occasion to promote the statistical literacy. Thank you.
Let me thank again Professor Giulio Magli and Professor Corrado Crocetta, and may I invite Pedro Delicado, Professor Pedro Delicado from Universitat Politècnica de Catalunya to join us for the first talk today.
Sorry, one moment. I close this because it's personal. Okay.
Yes.
Okay, and to enlarge.
I suppose I stay here, no?
And to
Because
You
I
would
need.
love to stand, don't
Yes,
you?
because I need
Okay,
the microphone, so it's not possible to. Yeah, but it's not possible to.
You
be,
would like to have a microphone?
No,
No. Gelato?
No, no.
We can if you
Okay.
want.
No, it's okay.
Okay.
I think it's good.
Sono dalla regia. Okay.
No, it's okay.
So Professor Delicado will talk about wildfire vegetation recovery through satellite remote sensing and functional data analysis. Thank you for being here.
Thank you very much. First, I would like to to thank Laura for the invitation. Yes? Okay. Thank you very much, Laura, for the invitation. And I will present this joint work with Feliu Serra and Fernando Cucchietti. This is part of the PhD thesis of Feliu that was co-advised by Fernando and me. The outline of the talk is this one. I will start with an introduction and background. Then I will present you the data, the methods and models we have used, mainly two techniques, synthetic controls and matrix completion, and functional on scalar regression. And then I will present the results and some conclusions. Okay. Wildfires are becoming an increasing concern with the rise of temperatures around the globe. This is especially important in California for the last decades, and this is the area we will study in this work. We focus on California, on wildfires of California. And we take advantage of the information we can take from remote sensing, that is generally understood as the measurement of Earth through satellites. Earth has been monitored from the space for many decades. Oh, I'm okay. Okay. So, and in particular, satellites are useful for taking information from the evolution of wildfires, not only during the time of the wildfire is active, but in the years after the wildfire, in order to be able to measure the recovery of the land. So. Remote sensing helps us to measure the risk conditions of pre-fire in the pre-fire period, and then help us to map the burning area after the wildfire, and we are able also to measure the severity of the burn of the wildfire, and also to monitor the post-fire vegetation recovery. Understanding the wildfire effects and post-fire recovery can help improve the prevention, land management, and vegetation recovery planning. We, from satellites, we are using mainly the Landsat satellites. Okay, so our scientific questions in the whole thesis of Feliu Serra about wildfires, vegetation, and remote sensing are the following. We asked what are the effects of wildfires on vegetation and on different kinds of environment. Also, how this effect depends on the characteristics of the burning land and on the vegetation that is present in these areas. We also ask about the period of the effects, about if the effects of the wildfires has changed with time. For instance, if the wildfires has more severe effects maybe 3 decades ago than now. Also, we monitor the cycles, the seasonal cycles after the wildfires, and study if they have changed after a wildfire. And the most important in this talk is if we can explain the dynamical effects of wildfires and vegetation recoveries from characteristics that we can measure in the burned regions. Here you have an image of satellite image of the same area before and after a wildfire. And you can see here the wildfire is affecting this area here. So in the image we take from the satellites, we essentially measure light reflectances, and these light reflectances in different wavelengths can be combined in order to define vegetation index, the most common of them being the NDVI. And if you monitor the NDVI over one area, you can have before a wildfire something like that. you have seasonal patterns, but when the wildfire happens, there is a sudden decrease in the vegetation index, and then it starts to recover little by little with also maybe some seasonal pattern. So what we want is to measure the effect of the wildfire in this decrement of the vegetation indexes, and we want to measure that also in order to make causal inference. We want to establish that the effect we are measuring has been caused by the wildfire. In an ideal scenario, it would be perfect if we could observe the same place with and without burning at the same time periods. But it is impossible because we would need to have two copies of the same landscape and have two versions of the reality with wildfire and without wildfire. Given that this is impossible and that we are not able to perform a randomized control trial, we need to find a quasi-experimental setup. And the tools that we will use are synthetic controls. That is a methodology that perform causal inference. Synthetic controls consist on trying to recreate an artificial area that before the wildfire is performing very similar to the area we are studying, and this artificial area is not affected by the wildfire. So if we let this artificial area to evolve on time, we will have some pattern corresponding to or approaching to the pattern that we will have in this area if the wildfire has not happened. So once we construct this synthetic control, we measure the effect of fire as the difference between the synthetic control and what we have really observed in the burned area. So this is the effect we want to measure. Okay, so the data we are using are part of the data are coming from remote sensing, and as I told you before, from Landsat satellites. And in this, from these satellites, we study mainly three vegetation indexes: the NDVI, Normalized Different Vegetation Index, and two more indexes that measure the width of the areas. The results I will present are coming from NDVI, and this is just a combination of the light reflectancy at different waves, different wavelengths. This is the near infrared, and this is the red, and we take this operation, and this index is a good proxy of the vegetation in the observed area. Here you have an example. This is an image before the fire. This is the same image after the fire, few months after the fire, and this is a couple of years after the fire. So we can see that the fire makes a drop suddenly the NDVI, but little by little it is recovering. So we are trying to measure this landscape recovery. Okay, additional data sources are also used. We use also the monitoring trends in bar severity. That is a program that provides many information from the wildfires in the United States, and mainly we use the perimeters of the wildfires larger than 1,000 acres. And we also have information from meteorological variables that will be used as explanatory variable for trying to explain the dynamics of the recovery. So this is the map of California with the areas that has burned at least once from 1984 to 2016. Okay, so this is the same area, and we focus on only on wildfires that has burned only once, and this is mainly because the methodology we are used is appropriate when you have only one intervention in your statistical units. So in this case, intervention means wildfire. So these techniques that we are using, these synthetic controls, is ready to be used when you have only one intervention. So we limit ourselves to these 2,043 wildfires that burn only once. Okay, in addition to measure the vegetation indexes in the burned areas that here are in red, we also study the areas surrounding the burns, the burned areas, in order to have some control areas, because these the control areas, the control regions around the wildfires are areas that are similar to the burned regions, and that has not suffered any wildfire during the studied period. So each of these areas is summarized taking the average of all the pixels that belongs to this area. So for instance, for this wildfire, we will take the average of the NDVI index of all the pixels belonging to this area, and we have one observation of this variable every 16 days. So we have time series observed every 16 days. That is the period of the satellite covering this area of California. Okay, so I will talk a little bit about synthetic controls, not too much, but this is a methodology that was proposed in 2010 and 2015 by Abadi and co-authors, and they try to fit a model like this one, a simple model, where we have observation of different units I over different times t, and the outcome of this, the variable of interest, can be explained as a function, a linear function in this case, from explanatory variables. We assume that there is also latent factors, a latent factor specific for each individual, and another latent factor evolving on time. And additionally, there is a term that takes into account if this unit has received the impact of an intervention in general, in this case a wildfire, and this indicator is 0 before the intervention, before the wildfire, and is 1 after the wildfire. So this coefficient here is measuring the effect of the wildfire. So this is the most simple models, and this is what is estimated by synthetic controls, and also by the generalized synthetic control proposed by Xu in 2017. But we will use another version of this technique that is given by matrix completion, and this is proposed in 2021 by Athay and co-authors. So in this approach to the same problem, we consider each row of the data matrix is corresponding to one of the wildfires, to one of the statistical units, and each column is corresponding to each time period. Okay, so we have rows are time series, and when one of the rows, one of the studied areas suffer a wildfire, we put the following data as missing data. So we will have some of the rows with missing data from one column until the end, and other rows that are complete because they are corresponding, for instance, to one of the surrounding area, to the control regions. So we have this matrix. Some rows are complete, other rows are not complete. So we try to solve the problem of estimating the counterfactual, the synthetic control for the rows with missing values by using a matrix completion technique. So we will solve the problem of complete the missing entries in this matrix, solving a penalized least square problem. So we are looking for a matrix L such that it is similar to the observed data in the position at which we have observed data, and it is simple in some sense because we penalize by the nuclear norm, okay, of this matrix, the sum of its singular values. So if we are able to solve this problem, matrix L will be complete, and the position of matrix L that corresponds to the missing entries will be our estimation of the synthetic controls. Okay, so I will show you an example. I will take just a wildfire as an example. This is the wildfire that is called MEU Lithium Complex. It corresponds to a wildfire in Mendocino County, year 2018, and it was a medium-sized wildfire in evergreen forest. So the NDVI we have observed for this area before the wildfire was this one, and after the wildfire we have this drop, and then the continuous recovery. Okay, so what we want to do is to estimate what will be the continuation of this time series if the wildfire has not happened. So this is what we do with this matrix completion method, and when we put this wildfire will be one of the rows of matrix Y, and after the wildfire we will have the data we have, and then we will have missing. So this is entering in the matrix Y, and what we recover later by matrix completion is this green time series, and the difference between the green time series and the red one will be our measure of the effect of the wildfire. So here you have the difference between these two things. Before the wildfire, these two time series are very similar, and after the wildfire, we are able to measure the effect. But in this effect, in this light green curve, there is also seasonality and there is also noise. So what we want to do is to take a kind of a smoothing of this effect obtained by matrix completion. And the way we do this smoothing is as follows. For each wildfire, we take the 7 complete years after the wildfire. Okay, so we consider this time series, and we decompose this time series as in the structural decomposition, trend, seasonality, and irregular term. And we will use, in this case, we use LOES for estimating these three components, and the trend is the element that we will consider that is really the effect of the wildfire. So in this case, we decompose the light green curve into these three components: trend, seasonality, and irregular component. And this smoothing we have here is just the trend obtained by this the composition of the time series. So here you have the graphic of the 243 recoveries of the wildfires. Okay, so we have in this way we will have a functional data set. Each data corresponds to the dynamic of the recovery of one of the wildfires. The wildfire that we have used as an example is this green curve, and the mean function is the blue one. Okay. So given that we have this functional data analysis and that the effect of the wildfires are measured by this functional data, we want to explain, we want to explain the effects from variables that we can measure before the wildfire. So we will consider pairs of variables. The part X is just a set of explanatory variables that we consider not evolving on time. and the y, the response in this case, is a functional variable that are the recovery dynamics. And then we will fit a function on a scalar regression, at which the response is a function and the predictors are scalars. This is the standard the linear function on a scalar regression model, but we use a model that is a little bit more complex, that is a functional additive mixed model that was proposed by Scapel and co-authors in 2015. And in this model, the explanatory variable can enter in different ways. They can enter just as a linear term not varying over time. They add just a constant to the response function. Maybe they enter in a non-parametric way, but just in a constant way over time. We also allows that they enter as in the previous linear function on a scalar model. The coefficient is a function of time, or we consider the possibility that they enter in a non-parametric way jointly the time and the values of the explanatory variable. So we have different possibilities. We also estimate a functional intercept. So in order to fit this model, to fit a model at which we try to explain the recovery dynamics, we consider several explanatory variables. First, we consider for every Barnett area, we compute the average NDVI over the 5 years before the wildfire. We compute this average, and we also compute the standard deviation, because standard deviation is also it will be larger for areas with a high fluctuation over the year, and will be lower for instance, for evergreen forests or for areas which are close to be desertic areas. We also compute the entropy of land cover, because land cover can be of different types, and if there is different species in one of the areas, maybe the recovery is different. We also take latitude and longitude, and the month and the year of the moment of the wildfire, and also the size of the wildfire, the elevation, and also several meteorological variables. The maximum temperature in the 5 years before, rain, solar radiation, and Barnett index. Okay, so they are our explanatory variable. So first we do a step of variable selection and also term selection, because each of these variables can enter in a global model in this different way. So in order to select the way to put a particular explanatory variable into the model, we have studied in 55 separate models, univariate models, which is the proportion of the explanatory variability in functional scalar regression model that use only one explanatory variable, and we use one model taking this way, the explanatory variable entering in this way, another model entering this way, another model entering this way, and so on. So then we decide for each explanatory variable, we decide in which way and we put we enter the variable in the model, selecting the way that has larger percentage of explanatory variability. If they are very similar, this one and this one are very similar, this one is a little bit larger, but this one is much simpler. So if they are very similar, we prefer the most simple term. So performing this selection variable and terms, we finally decide to put in the final model all the variables in this non-parametric way, except average and standard deviation of the NDVI that enter in this way with two terms, and also the rain that is also entering in this term. The global model is able to explain around 73% of the of the total variability. And here I will show you the coefficients we have estimated. For this, here there are average and standard deviation. So we have two estimation of this coefficient depending on time. There is also another function, another coefficient depending on time corresponding to rain, and there is also another coefficient depending on time for the intercept. So we will have 4 coefficients depending on time, and they are these ones. The intercept is this one. This one plus this constant. If we take this curve, that is the functional intercept, and you subtract this constant, then you obtain more or less the average of all the wildfires. Okay, and let me comment a little bit. This is the coefficient corresponding to the average NDVI in the 5 years before the wildfire. So all the variables are entering has been normalized to have 0 mean and 1 standard deviation before entering the model. So if you look at this model and you remember what we are telling, this term here, imagine that for one area the NDVI is 1 standard deviation larger than the average. Okay, so for this area, the extra contribution of this term is just the coefficient we are estimating, is just this coefficient. So for this area having NDVI, average NDVI, 1 standard deviation over the average, we will have that at the beginning, the drop in the vegetation in the first year is larger than the average, but from 1.5 years, it is recovered in a faster way than the average. So large values of NDVI make faster recoveries. Okay, and for the standard deviation and for the rain, it is a little bit more complicated. You can see that they are almost constant except for the first 2 years, and it is also you have seen that the scale of these recoveries is quite small in comparison with the results I will show you later, because I will show you now the shape of these non-parametric functions. Remember that each of these variables entering in this way is given this function that is not depending on time. So, and the estimation are as follows. Let me talk a little bit about the average NDVI. And for instance, think in this area before that has 1 standard deviation over the average in the average of the NDVI. So this area for all the period will have around 0.05 value 0.05 lower than the average. And additionally, if you take the dynamic effect, it will be recovered a little bit faster after 1.5 years. But it is not. It is quite complicated to combine these two different things. And but if we look only at this constant effect, you can see that the areas having low NDVI suffer less than areas having larger NDVIs. Maybe because if one area has a large NDVI, there is much more vegetation to be burned, and then you can lose much more than if it is a poor vegetation area. And the opposite happens for the standard deviation. In areas where you have more variability, then the loss in vegetation is lower than in areas with a small variation in NDVI. The elevation is also relevant. The areas with high elevation suffer more than areas with low elevation. And also it is interesting the year. The year is almost constant, so with this data having just 30 years of of observation, we are not able to appreciate any change, any climate change. There is also no apparent effect of the month, of the season at which the burn is appearing. And also the rain is affecting more or less like the standard deviation of the NDVI. Areas where more rain suffer less than areas with low values of the NDVI. So we conclude that we have used a methodology creating synthetic control, which is an effective way to construct valid counterfactuals, and we have been able to explain effects and vegetation recovery from wildfires. We can say that on average, recoveries from large wildfires are slow and take more than 10 years. And conditions such as elevation, homogeneity of the vegetation, low precipitation regimes, or places with large maximum temperatures are more severely affected by wildfires. But each particular wildfire is a combination of a unique set of conditions that alter vegetation and ecosystem in a different manners. And, okay. I have lost the last slide. Yeah, I don't know why. Oh, here it is. So thank you very much. And
well, thank you very much, Pedro. Very interesting talk. A lot of things to be done here, looks like, with functional data analysis and spatial statistics. In fact, my question goes in the direction of spatial dependence. Looks like you start with your matrix of observations, discrete time series. For each row, you have a site that you have observed a long time. But presumably, you're taking sites that are not very far one from each other. So I wonder, how do you take into account spatial dependence in your analysis? It doesn't look like it's playing any role, right?
No, we have not taken into account the spatial dependence.
Okay.
It is implicit in the analysis, because when we try to
Exactly.
complete the rows, this method take information from the rows that are complete in order to fill the gaps in the other rows. So if two rows are corresponding to sites that are close to each other, one of them may help to complete the missing observation for the other.
So in fact, my question was in this direction. Do you envision the fact that we can sort of expand on this in order to take into account spatial dependence when we do?
Yes.
Exactly, when we go through this step?
But our experience is I have not explained that here, but our experience in the whole thesis of Feliu Serra is that one alternative approach that is for each wildfire considered as a control region, just the border, and try to fill to estimate the evolution of the wildfire, taking into account the control region that is just around it. This strategy is worst in practice.
Okay.
We have compared both strategies, and matrix completion performs much better in the sense that what we are able to recover before the wildfire are much closer to the reality that the other way around, to using just the borders of control regions. So I don't know, but maybe if you want to use a spatial dependence, maybe the winds are not so large.
Okay.
But we have not checked that.
Okay, thanks.
Well, first of all, thank you very much for the presentation. It was very clear, even for a non-expert of these matters as I am. I have clearly just a curiosity on the model selection part, no? That you showed very interestingly how one can compare let's say, the constant effect against functional versus parametric, non-parametric. Very interesting, indeed. I just have the feeling that when the variables are collinear, highly correlated with each other, maybe, what you do is like you condition on the simple one variable model.
Yes.
So perhaps it could be that if you take, different points in the model space, you get different answers.
Yes.
Clearly, it's difficult.
Yes. This is a very heuristic approach. The literature for model selection, let me see, in this standard linear function on regression model, there is some literature on model selection, but at least at our knowledge, there is no literature on model selection in this functional additive model. So we do our best. We try this way, but I know that it can be do better. Yes. Yes.
Hey. My question is, I'm wondering if you ever tried this model to predict how a new fire, an unseen fire, how the recover from an unseen fire will perform. So in terms of inference of, predicting how the vegetation will recover with a new fire.
Yeah, we have not do it because our data set was, at some moment we closed the data set, so we have not considered wildfires that has happened a few years before the closing of our data set. But we have performed some kind of cross-validation, and the results was not so, was so. You can predict, but our experience is that in cross-validation, the results were not were regular. No, we have not tried to predict. We have this percentage of explainer variability, but if you put this is a kind of R-square, but in the training sample, we have our experience when you put something in a test sample is that the results are worse.
Pedro?
Yes.
Thanks for the interesting talk. And probably my question is a bit related to Pier Cesare question. Because, of course, this is a general regression function, and there are similar models in healthcare research, of course. In similar models in healthcare research, where we are trying to estimate probably, say, the effect of pollution on, say, some disease effect. And the recent literature in the last year is stressing the possibility to include in the model a spatial random effect, as probably Pier Cesare was suggesting. And this is probably useful, apart from improving probably the fit of the model, but also since you are interested in estimating, in producing causal inference, the inclusion of this spatial random effect probably would be useful to overcome the problem of the bias you could have in terms of unmeasured confounders. And so I think it would be also useful to include this spatial random effect also for model interpretation, or for have a nice interpretation of probably of your random coefficients.
Yes, good. Thank you. Thank you for the suggestion.
I have a more question about the penalty, the penalization problem that you used to estimate the matrix compression technique. If I understood well, the results of this minimization was a little bit noisy, and you needed to smooth this.
We decided to smooth.
So,
Yes.
I mean, the smoothing could be, do you think that could be added a second penalty in this optimization problem to, you know, also smooth, so for example, penalizing differences
Yes.
or something like that,
Yes.
and also penalizing neighborhoods and
Yes.
handle space and time all together in the matrix compression?
Yes.
Compression.
Yes. It could be. Yes, yes, yes. But the question is that we try to use developed methodology. So we have used the matrix completion implemented by the authors of this paper. So in this sense, we just used pre-cooked tools. But you are right that including more penalty terms here, we could arrive maybe directly to this. Yes, you are right. Yes, thank you.
So let me thank again Professor Delicado.
Thank you very much. Thank you very much.
And ask Professor Passot to join us on the floor. Professor Passot from University degli Studi di Bergamo will talk about statistical modeling and COVID-19 impact on maritime carbon emission. Thanks.
So, good afternoon to everybody. So this is a joint work with some colleagues from the Mediterranean Center for Climate Change. You see here, it's a very applied work, and you can find more information. It's published here on Sustainability Journal, and also the data are open access, published on Zenodo repository. I will consider just a part of the things considered in the paper. Generally speaking, we have data about carbon emissions from ferries traveling in the North Sea, Baltic Sea, and Mediterranean Sea. And then this data comes from a public repository from the TETIS system, which is a database collected by the European Maritime Safety Agency. And then we have more information from about ferry parameters from IHS Market, which is a commercial database. So this is open access, this is not. We merged this data to build a statistical model enabling to try to understand the emission patterns during the COVID lockdown according to various regional factors and ferry type. So, I have the banana. Otherwise, I get okay. So the data structures is like this. We have, generally speaking, a change factor, and we want to test or understand, for example, the COVID-19 lockdown. And we have some data about the fleet characteristics, and we have. Okay, we don't have data. Brown here is missing data, okay? But we would like to have data about the traffic, and we have, okay, structure related to the geography. And as a consequence of human activity, we have a certain cruise patterns from the ships, and for each cruise we have, in principle, a voyage profile defining, say, the power needed, the fuel, and the carbon emissions, which depends, of course, on wind and waves, depends on meteorological oceanographic data. And this results in the pattern, the emission pattern. This general scheme, and we have some special papers related to, for example, this part on singular case studies, but in this case we are considering, say, a regional problem, and you see here the description of the data. We have only, if any, yearly data. We don't have, say, data at a single travel level. So we cannot answer all possible questions about the pattern of carbon, but we can answer some of them. So just to look in more details, the data sets, the public data set is collected, as I mentioned, by the IMSA agency. There is a regulation which asked the companies to collect emission data and to provide this emission data at a yearly scale. So this is a logical gap, because companies must collect for each travel the data, but they throw away the data and provide only the yearly total. So this is a kind of, maybe they say for privacy, but I don't know what is there. On the other side, we have private data at ship level with, say, ship characteristics and cruises. So the data set is like this. We have the public data set here, collecting both total emissions and emissions at birth. So these two things are quite different, because from the carbon point of view, total emissions are 10 times or more than emissions at birth, but emissions at birth are important for local pollution in harbor cities. So they answer two different questions here. I will focus, in this talk, I will focus on total emissions, not emissions at birth. You can find something in the paper that I mentioned. We have 3 years, because the regulation started operating in 2018. And, okay, we have 2020, which is the horrible COVID year. So this will be the year we use to understand the lockdown impact. Then we have the, say, private data about port calls for the same 3 years, and then information about engine power and age of the ship and length of the vessel and passenger capacity. These are essentially constant data. Okay. We put together these two data sets and build the Zenodo data set I mentioned before. We have about 300 ships per year here, 12 variables, so it's not a huge data set. It's a small one, but it says something, as I hope I convince you. So let's start with a very preliminary analysis of the data. Here in the y-axis we have carbon emissions per ship, and you see the 3 years, 2018, 19, 2020, and you see the box plots, no big differences between 2018 and 2019, and you can see a decrease here, but we see also a large variability. So the ship fleet is very heterogeneous concept. We have very small ships and huge ships together. So just a preliminary descriptive analysis gives a reduction of about 6,000 tons per ships, or minus 15%. And if we take a look at the total reduction, which is more related on the total carbon emitted in the atmosphere. So the climate change is here, 2.5 megatons reduction, which is different in percentage because, of course, the distribution of the data. So we asked 3 questions about this data. Did the heterogeneity of the ferry fleet influence the variation, and how? So the first is about heterogeneity of the fleet. The second question, was there any specific geographical pattern across the European Sea? So you see we have three regions, so we are trying to understand what is going on with respect to this point. And was the change related to the way the vessels were operated? We don't have much information about this, but we have the port calls. So we have some information on this point, and we'll try to answer this question. So to do this, we use a linear mixed effect model, which is, say, kind of special case of Pedro's more generalized functional linear mixed models. But here we try to deploy the interactions between the variables. So we have, say, a dummy variable here for year 2020. We have a categorical variable for the C domain. And we have a group of interlinked variables for the engine size, length, number of passengers, and age, which work as a group. And then we have a continuous variables for the number of port calls, treated as continuous. It's an integer variable, but it's a big number. Then we have a random effect here. We use both random intercept and random slope. At the end, the random slope was unuseful, and we stayed on a random intercept. And we have we focus on total emissions here as a response variable here. Using Wilkinson, I avoid math, detailed math description. Using Wilkinson notation, you see here the interaction between COVID and C. Then here we have a fifth order interaction, but with, of course, you know, stars imply also the lower order terms. So this interaction were singular, so have to be omitted. And then we have interaction with the continuous variables plus the random intercept here. It's not a huge model. But it's kind of detailed model which can be easily estimated on, say, 1,000 data, so it's meaningful. Which model to choose? Which model to choose? Because this model is good or not? Do we have better models or not? So we did a kind of extended cross-validation exercise, testing 40 models. Indeed, we tested more with the random slope too, but it's not reported here, the random slope testing. So the first part of these models are fixed effect models without the, say, vessel type pool, without this kind of information. And you see the worst case. Then we introduced the 4 connected variables here. We have EIC and cross-validation root mean square error, conditional forecast. Here they are very monotonic, and you see a big decrease when we add fleet information, so fleet heterogeneity is really important, and they are almost constant until 20. From 21st to 40, we have the same model with the additional random component. So you see that adding the random intercept improved the model relevantly up to this point that we use the vessel type. Once the vessel type is included, everything is more or less the same.
Okay, so we use equifinality approach. So according to this model with the same forecasting ability can be interchanged in a way. So, and we stop to model 30, and model 30 is indeed this guy here. Okay, the job is done. Now we can read the results, no big issues. So these are the most significant parameters found in the model. We see, the marginal effect of COVID is minus 4,000 tons. Here you see the interaction between COVID and the number of calls, which is an additional 1 ton per call. Okay, so this is a derivative. Okay, the other ones are this is a continuous variable. So this is a slope, and the other ones are, say, categorical variables, effect. So we see an important interaction between COVID and passenger capacity. We will see that for ships with large passenger capacity, there was a big reduction in emissions, larger than non-big capacity ships. And also in the North Sea, we faced a larger reduction. So these are the most significant results. In the blue line, you have the marginal effect of the North Sea, just to say that the North Sea is higher than, before COVID, is higher than the other two considered sea basins. So now we have the, say, computed effect for the different variables answering question 1. So considering the effect of the fleet heterogeneity on the emission reduction. Of course, we can say emission reduction or say traveling decrease. Indeed, it's almost the same thing, probably. In 1 year, we didn't have big technological changes, so this reduction is due to reduction of traffic, not improvement in technology. For high-power engines, we face a smaller reduction. For the low power, we have 35%, and for high power, only 14%. Consider that the pre-COVID averages are quite different. Of course, the high power have larger emissions than low power ships. So this number are quite it's important to read both the absolute value and the percentage. The number here is about pre-COVID observation, so it's about this mean here, but just to show that it's relatively balanced here. So for vessel length, we have that, okay, larger vessels had a larger decrease in absolute value, but a smaller decrease in percentage. So this is contrasting results if you look at the absolute value or percentage, of course, because the two sets have very different emissions. Again, considering passenger capacity, we have the, say, more striking difference. So low passenger ships have had a reduction which is about 1/3 of the larger ones. So this is very big in absolute value, and it's also important in percentage. So we see that, indeed, as expected, the fleet structure influenced very much the reduction pattern. Regarding question 2, that is the geographical point, we see that the Baltic and the Mediterranean Sea are very close to each other. Indeed, the interaction is not significant, so they are not considered as having different emissions, and the reduction is about 20%. And in the North Sea, we had a larger reduction, both in absolute value and in percentage, which is, you see, larger than the overall reduction. So the third question was about the interaction, the impact of the number of calls on the COVID effect, or if you like, the impact of the COVID effect on number of calls. Here you have the pink lines are during COVID, and the blue line are before COVID. We see that for the three C bases, we have more or less the same pattern, and this is different, especially when we have a small number of calls. So we have a big difference here. So the COVID impact was larger when the ship traveled less, or at least visited less harbors, because number of calls is the number of harbors visited by the ship per year. So it's the total. And then for a larger number of calls, we have little data. So I missed the picture with the standard error, but here you have larger standard error, of course, because you can see here we have little data. So, conclusions. Using the integrated data sets, we showed that the horrible year caused a reduction of traffic around 22% overall, and the model gives a larger reduction than the naive mean difference we could compute without modeling the heterogeneity in the fleet and in the data. The North Sea faced a larger reduction, while Baltic and Mediterranean Sea were not significantly different. Vessels with high passenger capacity were hit more than small ones. And also, some consideration about the conclusion of the study regarding the TETIS system. TETIS data are collected by companies on a per voyage basis, but only year totals are communicated to the European agency. This is a big loss of information. In my opinion, as also the President Crocetta mentioned, data availability, open data availability, it's a matter of, I call, the statistical democracy. So having this data would allow the scientific community and the people to improve the understanding of the emissions from maritime sector. So I hope that CMCC will try to act on the European agency to change this regulation, because it's really a bad thing to collect data and then throw away. Thank you. My last slide was thank you, but this has been deleted.
La congiura delle ultime slide.
Okay, so thank you very much. I was wondering, there is no time effect in this model because it's, of course, simple linear regression with random effects, I understand. But if you had more data, more time points, what type of model would you consider? I mean, I like the application because, as you mentioned it, well, we should have somehow the finer data instead of the total ones. Because, I mean, it's interesting, I guess, to see the change point in 2020, especially if we had somehow data in continuous time. So, can you just give us a preview of, in case you had let's say, total data, what type of models could you bring to us?
Okay, this would be, this is a quite standard model. So, of course, this component is important to handle the temporal correlation because the 3 years are correlated. We have strong correlation both in the response variables, about 0.9, or in the residuals, about 0.7. So we must do that. Okay, if we don't do this, we miss the p-values and the standard error computation. So the forecasting ability in cross-validation is very close, because if you go in cross-validation, the random effect is doing little from the forecasting point of view, but from the inference point of view, this term is fundamental. If we have a richer time information, we can enrich this component for sure. So we can put some time series here, and for example, seasonality, I guess, is really important. But we also can enlarge the conditional mean here. We can add more information about meteorology, for example, which influence very, very much the performance of the ship, especially the big ship against wind. They consume a lot of fuel more.
Maybe just one small other question, because we are running a little bit behind our schedule, although Professor Fassot tried to get us well ahead of time. You didn't notice? I'll tell you later. So.
Alessandro, we all know that all people working in environmental statistics have to face the problems speaking with stakeholders, try to meet, try to communicate results and to provide the best indicators, to be in touch with people also. So there is a problem of stakeholder engagement in this field. So you were mentioning in your final slides the difficulty to have the right data. So if you can just spend a few words telling us the difficulties to speaking with them and try to have a good quality data for your application.
Okay, try to answer. I try to see the glass half full instead of half empty. I'm going to present this talk tomorrow at CMCC in a European project. So with Interreg project, which has among its final results some recommendation to give to the European agency. So I hope that these kind words at the end of my slides will be useful for that.
So anyway, thank you, Laura, for inviting me, to give this, as you said, introductory speech to the round table. So it will not be a seminar, it will be more a sharing some ideas or provocations, if you want, that hopefully will stimulate some debate during the round table. But of course, from my own, please, you are part of the round table, which will be, of course, based on my experience and on my different perspective, maybe on sustainability and the challenges for statistics, okay? So first of all, let me start with sustainability, which is some sort of ill-defined or not very well-defined concept. And I'm quoting here Purvis and co-authors. You can sort of see that there is a problem with the definition already in the pictures that are showing for presenting sustainability. But more or less everybody agrees that there are at least 3 basic ingredients to define sustainability, or pillars or dimension. One is environment, the other one is social, and the other one is economic, okay? And of course, these 3 pillars are also embedded into the Sustainable Development Goals of United Nations, although introducing the development part also makes things even more difficult and gives a twist to sustainability that is also different from something that you will see today. So in order to be more clear about what the way I intercepted sustainability, I will plunge you directly on something that we did with a very transdisciplinary group of people here at Politecnico. This group is called Trespassing, and already the name gives you the idea that we want to trespass the borders of our own disciplines. This is a group of people where there are colleagues from the management engineering, from design, from urban studies, from computer science, and the idea was to study infrastructures or modern infrastructures and to develop competencies that enables the understanding and the analysis of infrastructures. Why infrastructures? Because we think that infrastructures are indeed the enablers of sustainable policies. And the idea here is that, in fact, modern infrastructures could harmonize the heterogeneity that characterizes our social or urban communities. Now, when you think about infrastructures, probably you are thinking about bridges or railways, but there are other type of infrastructures that we are also interested, and they are strictly interconnected with this. Of course, there is the mobility infrastructure, the transport networks, but also the healthcare systems and welfare and social infrastructures and digital networks, of course, sustainable energy networks. Many type of infrastructures, different type of layers that in fact are not like a cake, but in fact they are kind of often very well interconnected. Now the idea is that the diversity, or we would say variability, of the communities that are the communities of utilizers of the infrastructure is what characterizes the complexity of the management, the design also, and the management of this infrastructure. And in fact, we are not satisfied any longer by an infrastructure that sort of is designed for the average utilizer. We think that the infrastructure could harmonize diversity by being more local, by being more aware of the different communities and different types of people using this infrastructure. So we think that here there is an opportunity for us, or for statistics, because in fact the integration of different data sources produced by modern infrastructures allows for a segmented description of the needs of the utilizers, okay? And in fact, the big data could provide detailed and timely information about these characteristics of the different utilizers and the needs of citizen user of the infrastructures. Now, what as statisticians we are doing, where we are developing methods for statistical learning, and the idea here is that these methods should be devoted to improve the quality of the public decision maker. And that's one of the take-home message of the book that you saw before, although that book is written in Italian, that we produced during the COVID period, and was a lot of fun sort of narrating some of the experiences that we did in this perspective. The whole point is that we think that the future will be in producing or generating, designing precision policies that are not policies designed for the average utilizer, but are tailored for the communities or the segments of the communities that are more similar, okay? And the use of big data should help us in doing this. Now, the reference paradigm also is, of course, precision medicine. Okay, here you have a simple picture that sort of tells you the story. On the left, we have the classical clinical approach where there is one therapy that is good for all and obviously has positive effects on some, sort of neutral effects on some others, and negative adverse effects on others. Precision medicine aims at sort of characterize small groups, if not the individual, and to give a therapy to the individual that is tailored on his or her genomic profile, on what the person has done in the past, what are the food that he receives, and so on and so forth, generating a positive effect on everybody. Not by chance, this is the reference paradigm, because many of us contributed to the design of this joint research center between Politecnico di Milano and Human Technopole, which is a new sort of research hub for precision medicine that it's in the area of Mind, or of former area of Expo. And many of us are still collaborating. Actually, the joint research that joint research center now is headed by Francesca Ieva and Emanuele Di Angelo Antonio. So it's part of our culture, let's say, in the group here. Now, I mentioned statistical learning, and I want to be clear about what I mean by learning. By learning, I don't mean prediction, okay? Since I don't want to be totally self-referential, let me quote Carlo Rovelli. And I want to say that I agree 100% with what he is saying here in this book, Helgoland. The goal of science is not that of making prediction. Science also aims at presenting an image of reality, a conceptual framework where to think about things. This is the ambition which made the scientific thinking successful. If predictions were the only goal of science, Copernicus would not have discovered anything different from Ptolemy. His astronomical predictions were not any better than those of Ptolemy, but Copernicus found the key for rethinking all and for better understanding. I totally agree with this statement. So whenever I see learning, and whenever I mention learning, even if it's machine learning, I do not make the equation learning equal prediction. I think that there is, and here comes a provocation, I think that there is a large scope for the original 3 dimensions, let's say, of statistics, which are, well, first of all, descriptive analysis. What happened? And we saw 2 beautiful talks that connect to this. It's not just a matter, and in order to do descriptive statistics, of course you need to use modeling. It's not just a matter of bringing the data to the table. You need to organize the data, summarize, graphically represent, work on the data collected from very different heterogeneous sources, okay? Then, of course, there is also prediction. I'm not saying that prediction, it's out of the picture. It's one of the dimensions. And, of course, here we have an array of possibilities for building up predictions. We have what we call transparent boxes, like linear models, generalized additive models, whatever. But also we have black boxes. And now, just to simplify things, I'm sort of stressing the fact that on the left you have interpretability, and on the right you have performance. But that's not, obviously, it's not a dichotomy. Sometimes transparent boxes work even very well for performance. So that's of course my point. And finally, there is also prescriptive analysis. What shall be done to make it happen? When you have understood how things work, so when you have made your predictions, what do you suggest to the decision maker in order to reach a result. I think this is also part of statistics and what we are doing in our daily practice, okay? So given the fitted model, the prediction suggests the best choices, evaluate opportunities and limitation. And all of this should take into account the uncertainty quantification loop, because we have plenty of uncertainties in our analysis that we should be able to quantify. We have uncertainty that comes from the variability or the noise through which we observe a system. We have modeling error, of course. We have uncertainty that comes from computation, the discretization error, and then we have prediction error. And this is a loop because, of course, the decision maker should be aware of every single piece of this loop as a generator, a possible generator of uncertainty, okay? So I think that this should be sort of the scheme that sort of we should keep in mind when we think about the challenges of future statistics. Now, just to show you that I'm not just preaching and without trying to applying my instructions, let's say, I just want to give you an example where we try to follow this philosophy in order to create or to suggest precision policies. And it's a very, it's an example that sort of it's very close to us because after the terrible events in Amatrice in 2016, the Italian government decided to set up a unit, a task force actually, to work on not on protection from natural risk, but on prevention from natural risk, okay? We are pretty good in Italy for protection against natural risk. Something terrible happens, our protection service, it's pretty good in it. But why don't we act before that in the prevention from natural risks, okay? Now, natural risks are usually described as there are three ingredients or three factors that enter into the natural risk: hazard, exposure, and vulnerability. Well, in case of seismic risk, you cannot act on hazard. You cannot reduce the hazard from earthquakes. It's not realistic to act on exposure. I mean, if you look at this map, you can think there is a simple way to solve the problem in Italy: just move everybody to Sweden, okay? And the risk for Italians will be zero. But it's not practical, although that's what is happening, as a matter of fact. In the Apennine, people are sort of disappearing, as I will try to argument pretty soon. So the only possibility is to act on vulnerability, okay? And I'm really thinking not just vulnerability of buildings, I'm thinking about the vulnerability of social communities. So what I really would like to capture is the material, social and material vulnerability of Italian communities, the diversity I was talking about before, okay? Now, the assessment of the vulnerability of a community is of paramount importance if you want to design precision policies, if you want to be more specific about how should you act on a community in order to incentivize prevention, okay? But of course, defining social vulnerability is something that is very specific, both to the cultural and heritage of a community, and also to the type of risk that you are considering. So indeed, ISTAT, which is the, as you know, the official statistic national provider, has something that is called IVSM, Indice di Vulnerabilità Sociale e Materiale, but this is an index that looks only at socio-demographic quantities, whereas we thought that thinking about seismic risk, we should be more context dependent. And in particular, we thought that together with socio-demographic quantities, we should also consider the demographic dynamics of the communities in Italy, which are very different around the country, very heterogeneous or very diverse around the country, and also not only the age of the people and the dynamics of the people, but also that of the buildings, of the places where people live, okay? Because, well, an aging and demographically declining community living in buildings requiring significant improvements to be brought to safety is more fragile and vulnerable when confronted with a seismic catastrophic event. And this is exactly what's happening in the middle of Italy, in the Apennine, okay? So we wanted to create some sort of new index of social and material vulnerability, fusing together different sources of different data sources, all official data sources, and so on. Now, I don't think I have much time, so I will skip something that I hate, but I will skip some of these slides. But let me just show you, when I say diversity and variability, let me just show you what I mean. For instance, this is the index of the social and material the material vulnerability index produced by ISTAT, okay? On the right, look at the distribution of this index in different provinces in Italy. And of course, what you see is that when you move from north to south, there is the mean or the central part, the central reference of the distribution is going right, which is bad, okay? But it's not the only thing that you observe. It's also the variability that is changing. So it's not, the unit here is the municipality. It's not the case that all the municipalities in the south are the same. Indeed, the variability increases. Some of the municipalities in the south are pretty comparable to the municipalities in the north. It's just that in the north, the variability is smaller, and so you can take the mean as a reference, but that doesn't happen, for instance, in Naples or even in Palermo. So that's something we should take into account when we design policies that have as a goal to improve, to incentivize people to improve the safety of their home. Another picture I want to show you is this. Look at the population growth and seismic hazard. Look at the picture on the right. Here you have a curve, a logarithmic curve, about the population growth starting from 91, I guess, up to 2011, 2012, I don't remember. The orange curve is the municipalities where the seismic risk is very high. Those communities are disappearing, whereas the blue curve are where the seismic risk is very low, okay? Those are increasing. In those communities where the seismic risk is high, there are no young people, they are going away, but they left the old ones behind, okay? So how do you pretend to incentivize these old people to improve the safety of their house? Not with an average policy that is equal for everybody in Italy, okay? Age of the buildings. I mean, we have very old buildings, we have very new buildings in Italy, but unfortunately, the old buildings are also where the risk of earthquakes is very severe, okay? So overall, we produce then, this is a beautiful playground if you want to use functional data analysis, spatial statistics. This is another talk. I will not give you the details. I'll just give you at the end, we produced a sort of an index that was integrating these different dimensions. And just from the picture, you see how heterogeneous is the Italian representation. How, in fact, the red ones, of course, are the places where this social and material vulnerability is very high. It's not just the south, it goes also in the north. I mean, you need to be aware of this heterogeneity if you want to produce policies that are tailored to the community. Now, indeed, these analysis, we thought, supports a strategic redesign of policies. In Italy, in fact, most buildings are privately owned. Public policies aim at stimulating owners to improve the safety of their houses, should take the difference of the communities they act upon at their core, okay? For instance, what happened after the Amatrice earthquake was that the government sort of generated a law so that people were allowed to deduct 80% of their investment from taxes if they were improving the quality, the safety of their house. But these policies didn't have any effect because on those communities, people were old and poor. And so even an 85% of deduction was not incentive enough to improve the quality of the house. Now we move to 110%, but still it's not acting. They are simply too old. It would be better and less expensive for the government just to go there and just do it. I mean, without asking the private people to act. Do it, unless you want, of course, to have in the future an Italy where in the middle of Italy there is nobody, or it's just like a place where you go to see the beautiful monuments, but you don't live there. So sustainability, it's also this, I think, okay? So we can, through the big data, through our models, we can try to help decision makers to move from a generic approach to the design of policies to a precision approach to design policies. Now this, of course, calls also for the meaning of big philosophical ideas like what is equity now? What is fairness, of course? It's easy to say equity means same law for everybody. But what I'm saying is maybe we should accommodate to variability. We should follow variability. But then we need to reformulate what we think about in terms of equity and fairness. Okay, so just a few references for this talk. We produced, in that task force, we produced a beautiful, very interesting document, which you can find here. And of course, in 2018, the government changed, so that document is one of the closest of the Italian. Although that experience became a department of the government, and so maybe they will act. Mostly the pictures are taken from that paper in 2021 on JRSSA. And the book is in Italian, so maybe some of you can read it, some of you cannot read it or don't want to read it. Thank you very much.
Thank you, Professor Cesare. And before we go live with the round table, or the straight table as we have here, let me also introduce two other participants to the round table besides Professor Piacere Secchi, Corrado Crocetta, Alessandro Fassò, and Pedro Delicado. We have Luigi Ippoliti from the University degli Studi di Chieti Pescara and Rosal Bagnacolo, University of Torino. They are currently the president and the administrator of GRASPA, that is the permanent research group of the Italian Statistical Society devoted to environmental applications. So thank you for joining, and I give you the words for the round table. And please don't be shy, I'll come with the mic.
Well, I don't know how we should be organized. Presumably, we can start with a short I don't know, ideas, thoughts, provocations, just going. Well, since I started from here, maybe we can start from on the other side of the
Okay,
of the
I'll try
table.
to follow you. Yes, Cesare. Yeah, you have put lots of meat on the fire, and so you have, I think, you have spotted very important words in your slides, and I can probably start from what is probably closer to our research, because you have mentioned big data and also precision medicine as a research approach. And probably we would like to say that nowadays we are living, or we are in the middle of an important digitalization process, no, as you have said also. And this leads to the availability of a large amount of data. And probably, I think it's not just a matter of big data. It's from the statistical point of view, is a challenge, the complexity of the data. And well, this is one of the best places probably, where I can speak about complexity of the of the data. And this is because the data impose several constraints. And from the statistical point of view, this is challenging because data come from different sources, and they come from with different scales in space and time, and probably this also leads to the concept of precision medicine, because maybe we want to use, in your view, we may want to use models which are able to produce forecasts at a finer scale, maybe going to individual, and also trying to grasp the large variability which is also present in the data. So to capture the heterogeneity Pier Cesare was talking about, of course we need lots of data, and we need richer models, and to estimate these rich models, of course, on the other hand, we need data. And we can, nowadays, we can try to exploit digital and non-digital data, which is not so easy to merge these kinds of data set. And also, if we want to stay closer to what people think, we have to face with data which are structured and non-structured data. So we also have seen the talk from Pedro. He was using images, and so we are probably all want to try to exploit information from images, text, and data coming from devices, smartwatches or other human sensors, and probably devices which are able to provide data about earthquakes. And we all want to try to merge this kind of data which comes from different sources. And this leads this is very challenging from the statistical point of view, because of course it's not so easy. There is a lot of complexity. But what about sustainability? To work with or to analyze such a rich data set, try to put all together and try to work with statistical models or, say, deep learning models. We know that in the last years there has been an important growth of data centers, which of course are based on intensive computing and a lot of energy consumption. So I think this should pose some question also about sustainability in a way.
May I?
I mean, we can follow any order.
Yes,
but,
yes,
you know,
yes. Yeah. I'm going with another provocation, I think.
Very good.
Thank you. Oh, I need to. Okay. Can you hear me? Yes.
Yeah.
Okay. So I thank Laura for the organization and Pier Cesare for this set of ideas and provocations. I agree, I would say, 100% with you. And I think in the context since we are statisticians, we think that the big data are an opportunity too, and that we could, we would like to use complex modeling and so on. And I agree that first of all, we need to go back to descriptive statistics in the sense that what we can discover in a data set, it's already there. And then we can put things in a very elegant way, but maybe we should aware that if we want that stakeholders and policymakers hear what we have to say, we need to find a compromise in our communication way to go. And also the provocation, the other provocation is be careful. It's not always true that we have big data with high frequency available. Okay, even for environmental problems where we think that everything in a way is observed, where we think that monitoring networks are there. We just we started a kind of collaboration with an environmental agency for problems related to water instead of air quality that I commonly did before. And things are very, very different because the legislation is different and oblige the government and the environmental agency to keep data, as in the case Alessandro Faso was showing us, to keep data yearly. Or they do report every 6 years. So our very nice statistical modeling or deep learning, machine learning, whatever, it's not useful. Clearly, we have to go back in this sense if we want to help these kind of precision policies, because if they have an instrument that is automatic, clearly they could collect maybe daily data, but when they go with the boat to the lake to measure something, then they have maybe 3-6 measures per year for pollutants that are important, otherwise even less. So the provocation is, are we sure we have or we can have big data always? I don't think so. Last point, because he was Luigi was talking about the energy we could consume with this high performance computing and so on. There's another point that in a project we are discussing even with Alessandro Faso, is the digital footprint that we have to put on the table in terms of sustainability. And I think I'm not the only one taking a picture every second to my baby girl, right? And then we have a lot of files on our computers, and then we buy another hard disk and so on. And if we do the same with all the kind of data we could collect, we risk to have this digital footprint very, very, very large.
Okay, thank you for inviting me also to the round table. I was not expecting that, so I have not anything prepared, but I have liked very much the presentation of Pier Cesare, especially in this idea of precision policies in parallel to personalized medicine or precision agriculture. I think it is very interesting. And I will just make a comment on one of the slides that has presented Pier Cesare, where he confronted white boxes, statistical models that are easy to interpret, with black boxes coming from machine learning that are impossible to be understood or to be interpreted. And in the last years, I have been working a little bit on what is called interpretable machine learning. And I have realized, and maybe you also, that this is a very interesting area where the connection between statistics and machine learning can give very promising results. And additionally, that a statistician must be aware, because our models are no longer the only ones that are interpretable. So models coming from machine learning joined with interpretable machine learning techniques can give better prediction than our statistical model, and also similar interpretability, or even similar explainability, or giving ideas about how a specific decision has given for a specific individual in one of these machine learning models. So we have to be careful about that, because people from machine learning is coming, and okay. Yes, and in principle, no more ideas. Thank you.
Before I need to thank Pedro, Alessandro, and Pier Cesare for their fine presentations. And I also want to thank Pier Cesare for this unusual way to do a round table, because every one of us was unprepared to this. And this is exactly this is exactly
my fault. I apologize.
No. This is exactly what I'm trying to do for our meeting, our CIS meetings, but people are not prepared to this kind of way, because I think it's important that people think about the future of statistics, the new developments, in this informal way as we are doing now. Then I try to react to some keywords you gave us, because otherwise I will be too long and we don't have time. You speak about precision policies. I completely agree with your idea, but I will translate your words in with some small change. We are thinking about impact evaluation. Ministro Giovannini said in one of the other editions of this virtual festival, is saying us that it is very important for our country that statisticians do their work. Then say doing impact evaluation, and I'm thinking about ex ante evaluation, ex post evaluation, and continuous evaluation. There is a great need to evaluate the policy of our country, but for this we need, Alessandro, I will repeat many times, we need data. We need the right data that will be available in the right time. We cannot do impact evaluation without data. Otherwise, we can ask, the future. We just we do some guess about the future. Then you speak about sustainability pillars. You know that CIS has done a new group that is called CIS-DS, and this is a good occasion to ask all of you to ask to be in this group of the CIS, and we approved the first position paper. In this first position paper, we say that sustainability must be connected with complexity. And it's important to follow complexity approach in order to understand what is sustainability. Otherwise, we think what Pier Cesare was saying. We cannot use the same suites for everyone. Every town, every region needs the right solution. And for this, we need data once again. We need to take into account of variability, of uncertainty. And we must do our work. Our work is to use the prevention instead of doing protection. And our work is to evaluate risk. I think that statisticians must work more in that field, because we are not so interested in this very important and very promising field. And so we have to do a lot more about that. Then another information to all of you. Pier Cesare is speaking about statistical learning. Then I will tell you in advance that in next week we will approve the new title of the conference that will be held in 2023, and the first keywords is statistical learning. So there is a great interest in our community about this subject, and I hope, once again, this is a kind of advertising talk, that all of you will come in 2023 in Ancona for our conference that will be about statistical learning. And you speak about also integration of different data sources. I've worked with Instat and with the Italian Authority of Ports in order to integrate data. They have a lot of data, good quality data, but we cannot integrate them. You know why? Because of privacy. Privacy is a kind of monster. And I was with the general of Guardia di Finanza last week, and he was saying we cannot do this project because of privacy. So we start to think also in a different way, because the protection of the privacy is very important, but cannot be a kind of obstacle to everything we think for the future of our country. So we must work hard in these directions. Thank you. Thank you.
Adding just a few comments. It's very intriguing, the idea of precise policy. Maybe regarding the connection with precise medicine, can be a big difference in my opinion, because precise medicine is based on the personal data, and I'm afraid that a policy based on the individuals could be objected from, the law point of view, because the concept of equal rights nowadays are not shaped to allow this kind of approach. I mean, in principle, equal rights could be equal rights of being served as an individual, not in the same as you, but nowadays it's considered that everybody is equal. So maybe I introduce a little bit different concept. I don't know, because I missed maybe your point. I think that precise policy should be much related to not the individual, single individual data, but on the territorial data in high resolution, on social data, and on other kind of information that can be made kind of anonymous information, even are related to you. From this point of view, the current call of the PNRR, the next generation Italian call about extended consortia, partenariati estesi, has a specific line on sustainability, and there is a concept of georeferenced data platform that in principle could answer your point. I don't know if this will be the direction. I am in a team working on a proposal on that, and inside the team there is a debate about the data platform should be then kind of private product which can be sold on the market, or my opinion is should be public open access data to everybody, because if having open access data is a question about statistical democracy. Because I think that nowadays the pillar of democracy, the independence of powers, are not enough the old powers. Now there's the data power. So data should be independent from politics. And also something that has been lost in the last maybe 20 or 30 years, which is independence of the universities from the government,
freedom of research and freedom of teaching, which has been completely lost in Italy in the last 20 years. So this should be the direction, because the university should be allowed to critique the government, but to do in a proper way must have real data, not fake data. So this is a big issue which the Italian Statistical Office knows very well, and for many things is covered, but for the new big data, it's an issue. Maybe many times it's covered by privacy. For example, my example before about shipping data, why they are known only at total years? Because the big companies don't want to tell everybody what they do.
That's right.
And so it's covered. I stop here.
Alessandro, you were talking about ship data, but as Graspa Group, we asked many times data to the Istituto Superiore di Sanità to try to analyze data on the COVID, and we couldn't have any useful data. No, we have assisted really to a growth of papers on COVID, but at the end, it's very difficult to interpret the data and try to make useful conclusion about this kind of work.
Yes, I could not, resist myself from, coming to the round table because it's very interesting topic. Well, very difficult, but clearly Pier Cesare is very right. We should go into the direction of prescriptive analytics or precision statistics, however you want to call it, because the world call on us, essentially. We have to make decisions, and these decisions are nowadays supported by tons of data. Most of this data is interactive, it's based on feedback, so we clearly must go in that direction. However, it's not so easy for the statistician, because as Pedro pointed out very clearly, we are not the only ones that do this job, and this is correct. Clearly, it is a job that involves many other communities, data scientists, of course, engineers, but even politicians that often, make the predictions not based on data, but based on, let's say, insights. Let's put it this way, sensations. But the question, in my opinion, is that we should take responsibility as statisticians, and I think we should suggest the rules of the game, because we have to be able to compare alternative approaches, not necessarily only predictions, which are easier to compare, but also descriptions, explanations, simulations, in terms of principles. So I think we should engage in the job of formulating principles that belong to the history of statistics, like robustness, precision, explainability, maybe even fairness. Those principles, I think, are very important and should be part of our job in the future, because we're going to go into a world where predictions, the explanation, descriptions will come from different angles, different disciplines, different perspectives. So we really need, let's say, metrics to compare. That is my sense on this. I don't know, maybe I'm wrong, but I think we should go with it. Thank you.
Hi. I was wondering if, for you, is more important having big data, because big data sometimes come with big noise, or with good data. So you see, if it's more important stressing more the fact that we have to collect good data, maybe smaller in dimension, but good, and working on models that are, like, for example, compact and more explainable, and allow us to combine performances, so generalization ability with explainability, because I don't think it makes sense putting generalization and explainability into two separate worlds. They must go together always. Otherwise, we don't do a good job, in my opinion. So I don't know who can answer this.
I don't know. I think it depends on the context. It would be nice to work with lots of data. Of course, we need no noise, but this is not possible, of course. And from the statistical point of view, as a statistician, I think we should be able to provide models which are able to model the propagation of the uncertainty and also the noise inside the data. I think we have all the tools to estimate the noise in this case. But I can also realize that there are some contexts in which probably the data and the problem is so huge that probably you don't need to understand what is going on, because probably the data are so large that it's impossible to go through the data and try to understand what is going on, or try to look at the phase of the number. Anyway, so in that case, I think all the tools provided by the machine learning community, I think is just work. It's just probably they try to exploit the correlation, and you get the results. Probably that is enough in some context, but not in other context. In other contexts, maybe you need to explain, and because people are not just happy if you say, okay, prediction is good. Many people want to know why you have achieved this kind of prediction, and how the model works, interpretability of the parameters. In some contexts, this is important, but I can understand. So I think it's important, the kind of problem you are considering. Yes, in medicine or in probably in management or people working in industry, they want to know why you are achieving some results or why the process is working. But maybe if you work with social data or with big data downloaded from the internet, maybe it's probably impossible to explain. I don't know. It's
something to say about bias, but maybe.
How can you say that?
If you don't say it, I will.
No, I was about starting to thank you because you reminded us that averages can hide more than extract information. So I think it's a good way for us as statisticians to look at the future, looking more to variability and uncertainty. I think that this is safer for our identity as a statistician to look at uncertainty. And talking about uncertainty, I think that the same issues that was just now raised can be also named something like selection bias about the quality of the data, and these underlying issues that nobody is still, I think, very sure to rise because we do not know still how to face it. But I think it's time to talk about that too, and trying to find the new way we need to avoid that the big data that are useful, we can deny that we have to use it, but they can be very biased. Big data, it's big bias. Big data might be big noise. So I think that this is the further provoking we need today. Thank you very much.
Thank you. Oh, yes, please. Well, thank you. So plenty of ideas, I think, and then
hopefully I was able to sort of stimulate some discussion. And I will start from the last thing what was said. I mean, most of the people out there in the industrial setting or when you work with companies and so on, they think that big data means unbiased because it's big. Basically, it's the entire population. So why should you worry about this? And I think that bias is one of the first things we should think about when we talk about big data. And so that Fulvia's comment, I think I totally agree with it. Of course, when I was referring, and this is very important if you want to base precision policies on the analysis of this type of data, because you could go terribly wrong in the sense of sort of capturing the bias that was in the data as part of your policy, okay? Now, of course, when I'm saying that precision medicine is sort of a paradigm, I'm not thinking about policies that reach the single individual. I'm thinking more in terms of communities. As I said, for me, the community was the municipality in the example I was showing you, but different type of communities. But the take-home message is, on one side, we have diversity, heterogeneity, variability among the different types of communities. On the other side, we have to act through policies and infrastructures on these communities. Now, we don't want to say, okay, everybody should be equal so that my policy will work well for everybody. People are not equal. I mean, there is a beautiful picture that Anna always shows us about the fact that, you are all equal and you're trying to look at out of a fence, and so the small ones could not reach the top of the fence. The tall one is well able to see what's happening behind the fence, and the middle one struggles a little bit. Okay, we can have steps so that everybody is able to look out of the fence. This is sort of precision policy in a very simple and graphical way. I don't have the picture with me right now. The idea is, of course, this requires sort of a rethinking about what we mean by equal and what we mean by a fair policy, okay? Because at the moment it's like equal, the same for everybody, but this means that the short ones will not benefit out of it, okay? Let me say short, just not to elaborate more, okay? Now, I totally agree with the fact that it's not just a matter of designing policy or using the data to design policies. We should keep always a lot of focus on the evaluation of policies. And I think this will be one of our goals as statisticians. We need to be able to evaluate also in order to change the policy dynamically. I mean, because maybe there is no problem, I would say, in admitting that you made an error and a mistake, but then you should change the policy if you are able to notice that there was a mistake. Otherwise, we will never change it. Totally agree with Pedro. Machine learning. I mean, when I say learning, for me, it's a very wide concept. I'm not trying to push the machine learners out of the picture. I think we are all part of the same community: statistician, data scientist, machine learning. Except that maybe we have different perspectives, different sensibilities. For instance, what Fulvia was saying about uncertainty. I put the uncertainty quantification loop on my slides exactly for this reason. I think that as statisticians, I always thought, I don't know, I start always with jokes in my courses saying statistics, well, what do you think is statistics about? And usually people think that statistics is about means, okay? All the jokes about statisticians are based on means, okay? From Trilussa on, okay? But I really think that statistics is about variability and not means. Means is just a way to center your reference system, and then you compute variability. So I totally agree, variability is our strong message as statistician, but the community is large. There are other people that do not qualify as statisticians that are doing similar. I don't want to build up fences between these communities. I think that we should all work together and exchange our different perspectives. So I'm not pushing out of the picture black boxes or machine learning algorithms, I think that they should be sort of incorporated and studied together with our basic principles that have been there for at least a couple of 100 years, because maybe there is something that is still wise on those principles. And finally, let me say, when I say big data, of course, I mean, especially in our community, I would say, but in our group, when I say big, I don't mean simply big in terms of sample size. I usually mean big in terms of complexity. So, I mean, most of us are working on functional data, object data, non-Euclidean data. So I totally agree. It's not just a matter of sample size. It's also a matter of complexity, but that stimulates new models, new perspectives, new ways of dealing with them. So totally agree with that. But I think I hope you have recorded this debate, because I still want to go back to some of the things you said. I think that it will be helpful for everybody, and also for the students who are here. Hopefully, maybe they will get some of the messages that we give in class, like, you know, jokes or something, are really related with something important that we are still discussing here in this at this table. So thank you very much for participating to this.
So let me thank Pier Cesare II and all the speakers. Let me thank Professor Giulio Magli, who kindly sponsored and hosted the initiative here today. And let me thank and give the words to Professor Corrado Crocetta, who joined us today and possibly wants to invite us to the Italian Statistical Society conference.
I know that I'm unpolite because you have to close the conference, but I want to say just a few words. Saying thank you to the organizer. Laura is one of them, because all of you have done a great work, and so thank you for organizing this edition of Verso il Festival della Statistica. Then just one word, because you were saying the same things. You were speaking about trapassing, but I prefer the word contamination, because I think that is a good idea. This is the proper way, a proper place to speak about contamination. But I want to say also a warm thank you to Graspa, that is doing a very great job for all our community. But I want also recall all of us that in 9 days we will be hosted by Fulvia Mecati, that is here in the first line, because she is organizing a new edition of Verso il Festival della Statistica, with a subject that is very important for all of us, women in statistics. So, see you in 9 days. Thank you.